One thermochemical equation for the reaction of carbon monoxide with oxygen is the following. 3 carbon monoxides, 3/2 oxygen gas, 3 carbon dioxides. And according to that delta H minus there, it releases 849 kilojoules of energy for that given reaction. All right, the thermochemical equation for the reaction using 2 moles of carbon monoxide. Well, it would just be twice as much, right? Oh, no, sorry, using 2 moles instead of 3. All right, so for 2 moles instead of 3, you would have to multiply all those values by 2/3, or 0.666. Right? So 3/2 times, or 3 divided by 2 times 0.66666. So that'd be 1 oxygen. And 3 divided by 3 times 0.666 would be 2 carbon dioxide, or 2 times 0.3, yeah, 3 times 0.666 would be 2. So that would be the chemical, or that would be the reaction there for 2 carbon dioxides, and our negative 8499 would also be multiplied by 0.666, and that's delta H would equal negative 566.0. All right, so there's the thermochemical equation for the reaction using 2 moles of carbon dioxide. What's the delta H for the formation of 1 mole of carbon dioxide? Well, it would be this divided by 2, which is minus 283. Okay, so that's 760, 283, 566, 212. Yeah. Okay, so 762. Magnesium burns in air to produce a bright light and often is used in firework displays. The combustion of magnesium can be described by the following thermochemical equation. How much heat in kilojoules is liberated by the combustion of 6.54 grams of magnesium? Well, if we have 6.54 grams of magnesium, we have to convert that to moles to determine moles of magnesium so we can use the power of that equation. So for every, how many grams of magnesium in 1 mole of magnesium? Look at the periodic table, 24.31 grams of magnesium for every mole of magnesium, right? So 6.54 divided by 24.31. All right, so that's 0.269 moles of magnesium. And the chemical equation says that for 2 moles of magnesium, we get 1,203, and we have that many moles of magnesium. We can go like this. For every 2 moles of magnesium, we get 1,203 kilojoules. All right, so take 0.269, times it by 1203 divided by 2, and that should be how many? 161.8 kilojoules per mole of magnesium. Right? Because well, that's just how many kilojoules we would get, and it's moles of magnesium are canceled out, and this is how many kilojoules we'll get. Yeah. All right, so that was 762. 762, 162 kilojoules of heat are involved. Methane burns with oxygen, so this is 764 now. (764). Methane burns with oxygen to produce carbon dioxide and water as a gas. The balanced thermochemical equation is down below. How much methane in grams must be burned to release 432 kilojoules of heat? All right, so we want 432 kilojoules of heat. And we want to know how many, what? How much methane? In grams. So grams of CH3O, CH4. Okay, grams of CH4. All right. Well, that's how many kilograms of heat we get, or that's how many kilograms of heat we want. We get 802 kilograms of heat for every 1 mole of CH4. And for every 1 mole of CH4, that's 12, 13, 14, 15, 16 grams of CH4. So if we solve this problem here, see my 764, make sure we're not missing anything, we should be able to determine how many grams of methane are required. So we have 432 divided by 802, and that's the answer in the back. Okay, we'll double check there. 764, 8.6. They have 8.64. Oh, because this is probably a little more than 16. Okay, good. 766. Construct an enthalpy diagram that shows the enthalpy changes from one-step conversion of germanium into germanium oxide, the dioxide. On the same diagram, show the two-step process, first to germanium monoxide and then its conversion to germanium dioxide. The relevant thermochemical equations are the following. All right, so we have a, we're constructing an enthalpy diagram. An enthalpy diagram kind of relates, we have on our y-axis here, energy, right? So we have germanium plus oxygen, 1/2 O2, right? And that's at this given energy, whatever that value is, some abstract value. I mean, it's not abstract, but we don't really need to define it. We just have to define the change from that going to germanium oxide, GeO2. This difference here is a -5, and minus is why we went down, 534.7. All right? Hello? It's by the tennis courts. Just, yeah. Right between, okay. All right, bye-bye, love you. Okay, so now they want us to draw the same thing, but just the conversion from germanium to germanium monoxide. Oh, sorry, this is not, for the conversion of germanium oxide to here, that's the answer. For germanium oxide to germanium monooxygen, right? This change here is minus 255. Kilojoules, right? Okay, and then if we go from germanium monoxide plus 1/2 O2 to germanium oxide, right? This value is going to be the difference between those two. Using this diagram, determine for the following reaction, germanium oxide plus 1/2 going to germanium oxide there. All right, so we see that this value here has to be the 534.7 minus the 255. So this difference is 279.7, and that's germanium monoxide plus oxygen to form germanium oxide. All right, so 279.7, which is 280 in the back of the book. Good. All right, so 268. Show how the equations can be manipulated to give delta H for the following reaction. All right. So we have these chemical equations with their values associated with their delta H's associated with them. And the chemical equation we want is 2NO going to with oxygen gas going to N2O4. So 2NO with oxygen gas going to N2O4. And we have up here N2O4 going to 2 NO2s, and we have NO and oxygen going to NO2. All right. The number here associated with this equation is a positive 57.93. And the number associated, the heat enthalpy change associated with the second equation is minus 113.14. All right, we need to get the N2O4 on the right, so we need to switch this equation. So if we flip this equation, make it 2NO2 going to N2O4, right? So we flip the first equation. That makes this a negative 57.93, right? Because this means going to the right, we require that much energy. Therefore, if going to the left or going the opposite direction, we get that much energy. All right? Now, if we combine that with this, I think that's going to give us what we want. So it's 2NO plus O2. Well, I don't have to rewrite it. It's exactly the same thing. So we just have to combine these bottom two here. Combine these, and when we combine them, we get 2NO, O2, and 2NO2s, yielding 2NO2s and N2O4. All right, the 2 NO2s cancel out, and then we're left with this last equation. So the delta H associated with this equation then is the sum of these two here. Minus 113.14 and a minus 57.93. 113.14 plus 57.93. All right, and that's a sum of minus 171.07. All right, so that's the delta H associated with it. I guess they just wanted to show how it was done. They didn't, oh yes, 171.07. So they asked for that. Okay, 68, 70. Calculate delta H in kilojoules for the following reactions. The preparation of unstable acid nitrous acid. Use the following thermochemical equations. All right. So we want to get HCl, sodium nitrate, HNO2, and sodium chloride. Sodium nitrite, not nitrate, nitrous acid, H2, and sodium chloride. That's what we want to get. How are we going to get that from the reactions above? Well, it looks like none of them have sodium chloride in them except for the first one. So we're going to have to use the first one, but the sodium chloride's on the wrong side. So we're going to have to flip it. And we're going to have to divide it by 2 because we don't want to have 2 sodium chlorides in the end. We just want 1 sodium chloride. And I don't see any other sodium chlorides in any of the other reactions. So we'll take the first one, the first equation up there, and divide it by 2. All right, and flip it. So if we flip it, that'll be Na2O, and then we're dividing it by 2, so 1/2 Na2O plus 1 HCl, yielding water and the sodium chloride, or 1/2 of a water and 1 sodium chloride. All right, so now we have 1 sodium chloride on the right like we wanted to. The of sodium nitrite. The second equation has the sodium nitrite in it. Right? I don't see the sodium nitrite anywhere else. So we're going to have to flip the sodium nitrite equation. I should write the delta H associated with this equation first. It's the 507 divided by 2, and then we change the sign because we reversed it. So it's negative 253.5. And that's kilojoules. All right? The second equation needs to be flipped as well to get the sodium nitrite on the left. All right? So, and we also looks like we have to divide that by 2 as well because there's no other sodium nitrates. So we'll do the same thing with the second equation where we take the NaNO2 and that is going to break down to yield 1/2 NO 1/2 NO2 1/2 yeah. 1/2 Na sodium oxide, Na2O. All right, so that's the second equation, reversed and taken in half. So we take the negative 427.14, divide that by 2, make it a negative sign, or that negative sign, yeah. So negative 213.57 kilojoules for that given reaction there. All right, so again, we took the 427.14, which was associated with the second reaction. We flipped the second reaction, divided everything by 2, changed the sign on the second reaction. Oh, no. This has to be a positive. It's a positive. It was a negative. We flipped it, so we have to change the sign and divide it by 2. This one's a negative, that one's a positive. Okay. So we have our sodium chloride we're going to get here. We have our HNO2. No, we don't. We have our NaNO2 we're going to get here. We have our HCl we're going to get there. So we need to get rid of this Na2O. Well, no, we got rid of that over here already. We just need HNO2 on the right, and we need to get rid of an NO and NO2. And that's good because, well, we have the bottom equation there. That'll give us our HNO2 on the right. We have to reverse it and divide by 2 again. I don't see any place where the HNO2 is anywhere else in any of the equations. So we're going to have to divide that one by 2 as well. So we just have to reverse that one and divide it by 2. So we have 1/2 a molecule of water, or 1/2 a mole of water, sorry. 1/2 a mole of oxygen, gas. 1/2 a mole of N2O, yielding 1 HNO2. Okay, so we took that equation, reversed it, and divided it by 2, so it's 34.35 divided by 2, 17.75, and we have to change the sign, so it's minus 17.75. So here's the first one, here's the second one, here's the third one. This is again in kilojoules. All right, and the last one. Right now we're going to have this here. We're going to have our sodium chloride from up here. Okay. Our sodium oxide is going to be canceled out here. Our NO2, sodium nitrite, is going to be there. So we have NO2 on the right and NO on the right. We have HCl on the left. We have this on the right, this on the right, this on the left, this on the left. We have our 1/2 mole of water that's going to be gone. But we need to have an equation that has oxygen and nitric oxide on the left. And that's our third equation, right? We take that one and reverse it. We don't have to divide by 2 this time, though, do it. Oxygen on the Yeah, no, we do have to divide by 2. We still have to divide by 2 because we only have to get rid of a half a mole of oxygen. Oh, but we don't have to reverse it. We want it on the right side. So we have to divide it by 2, though. So that's third reaction, 1/2 NO plus 1/2 mole of NO2 yields 1/2 N2O and 1/2 O2. That'll cross out the NO here. That'll cross out the NO2 here. That'll cross out the half mole of oxygen there, and we'll be left with the NO2, and that'll cross out that there. All right, so that should do it for us. Now we have to find the delta H of that value, that last one, which was the third one. We didn't divide it by 2, we just changed the sign by flipping the side. Oh, no. We didn't divide by, or we did divide by 2, but we didn't flip the sign. So it's 42.68 divided by 2, 21.34. But that's a negative. So let's make sure now, let's add all these up and make sure we get this down here. All right, we have HCl on the left, sodium nitrite on the left, HNO2 on the left, on the right, and sodium chloride on the right. Right? All right, so then we have sodium oxide on the left, and that's going to be canceled out here. We have the water on both sides, that's going to be canceled out. The oxygen on both sides are canceled out. The 1/2 N2Os are canceled out. 1/2 NOs and the 1/2